This is Jack Jackson. In this video, we're going to summarize some things and give a nice little table that kind of collects a lot of information about conic sections. We went over each of the conic sections, each of the types, in some detail in the last few videos. Um, so analytically, conic sections are second-degree quadratic polynomial relations in two variables. They can all be thought of as having the formula ax squared plus bxy plus cy squared plus dx plus ey plus f equals 0 for some real number constants a, b, c, d, e, and f. Now, if b is 0, then they have axes of symmetry that are either vertical and or horizontal. Ellipses and hyperbolas have two, and circles. Well, ellipses and hyperbolas have two axes of symmetry. Circles have infinitely many. Parabola only has one. But there'll always be either a vertical or horizontal line for the parabola and both for the others. But if the b is not 0, then some sort of rotation has occurred so that those axes are not vertical or horizontal. Uh, for the most, except for one thing, everything below I'm going to assume that b is 0. The thing I'm not going to assume b is 0 is this right here. There's this thing called the discriminant, b squared minus 4ac. It turns out that that is enough to tell you, looking at the sign of that thing, is enough to tell you which one of these types of conic sections it is. If that is a positive number, then you get a hyperbola. If it's 0, you get a parabola. And if it's negative, you get an ellipse, including a circle as being a degenerate form of an ellipse. I'm also going to mention this other thing here called G, which is you get by C times D squared plus A times E squared minus 4 times A times C times F. It's not that important, but I do want to mention it a couple times here. So if B is 0, another way to look at it is this. The parabola will be, well, of course, now if it's B 0, you won't have this term. A parabola will be missing either the x squared or the y squared term as well. So either the A is 0 or the C is 0, but not both. Okay. For an ellipse, you'll have an a squared and c squared term. Assuming the b is 0, you have an a squared and c squared term, a squared, x squared and y squared term. You'll have an a and a c that are not 0, and they will have the same sign. Okay, that in a circle, not only do they have the same sign, they're actually the same number. Okay, in a hyperbola, you get A and C have opposite signs. Again, this is assuming B is 0. Okay. There are some degenerations of this. If A and B and C are all 0, look what happens. You just get dx plus ey plus f is 0. You know that's a line. We've studied many things about lines before. Again, if A and C are both the same, the ellipse degenerates to a circle. The circle can generate to a point if this G turns out to be 0. It's like a circle with 0 radius is a single point. And if that G is negative, it's like a circle with a negative radius that just doesn't exist. For example, you know, x squared plus y squared equals 1 is a unit circle. X squared plus y squared equals 0 is just the origin. X squared plus y squared equals a negative number, not possible. No solution. Okay. A hyperbola, the formula can basically degenerate to two intersecting lines when the G is 0. We'll kind of see something about that. There's something called the eccentricity, and it's always 1 for a parabola. It's less than 1 for an ellipse. It's 0 for a circle, and it's greater than 1 for hyperbola. If you can kind of think of it as something to do with the curvature of the curve, uh, and at a particular point at the vertex, for example, and Uh, circle is your base model with 0 eccentricity. The ellipse, the more elongated it gets, the further it gets from being um, a circle, the more eccentric it is, closer it gets to 1. When it gets to 1, it leaves being ellipse and becomes a parabola. And then if you get even more eccentric, it becomes a hyperbola. Um, of course, the parabola is always exactly 1, circle it's always exactly 0. For an ellipse, it's c over the maximum of little a and little b, and I'll explain what little a and little b are in a minute. And for hyperbola, the eccentricity is c over little a when the negative's on the y square, and it's c over little b when the negative's on the x square, and that'll make more sense if you've been watching before with the formulas. Geometrically, these have definitions. The locus of points in a plane which are equidistant from a given point called the focus, and a given line not containing the focus called the directrix, that is a parabola. The locus of points in a plane for which the sum of the distances to two given points called the foci is a constant is an ellipse. The locus of points in a plane which are equidistant, the radius, from a given point called the center is a circle. And the locus of points in a plane for which the differences of the distances to two given points called the foci is a constant is a hyperbola. Okay, so the standard rectangular form in standard position is y equals 1 over 4p x squared. It opens up if p is positive and down if p is negative. Or x equals 1 over 4p y squared, opens right if p is greater than 0, left if p is less than 0. Now if we translate it, then we shift it by vector hk, translate it. Now it becomes y equals 1 over 4p parentheses x minus h squared plus k, or x equals 1 over 4p y minus k in parentheses square plus h. For an ellipse, it's the basic one is x squared over a squared plus y squared over b squared equals 1. So this one has a vertex at the origin here for the parabola. This has a center at the origin. Okay, that's the standard position. If you shift it now by vector hk, this becomes x minus h squared over a squared plus y minus k squared over b squared equals 1. The center is now hk. Horizontal radius is a, and vertical radius is b. When a and b are the same, this degenerates to a circle. X squared plus y squared equals 1 is the unit circle, or x squared plus y squared equals r squared is the a circle with radius 1. Then when we translate the circle by the vector hk, we now get the general form for a circle, x minus h quantity square plus parentheses y minus k close parentheses square equals r square. That's going to be a circle with center hk and radius r. You can think of that as a degenerate form of an ellipse where a and b and r are all the same thing. If we have a hyperbola with center at the origin, then that's going to be x squared over a squared minus y squared over b squared equals 1, or y squared over b squared minus x squared over a squared equals 1. Notice how I always leave a associated with x and b associated with y, both in the ellipse and the hyperbola. It makes things much easier. Some people do it a slightly different way, but I think this is much better and easier to keep track of. The one with the minus on the y square will open left or right. The one with the minus on the x square will open up and down. It is in two pieces. Now translate by the vector hk, and you replace the x by x minus h and the y by y minus k, and here you get the general form of the hyperbola. There is something called a polar form using polar coordinates, and this will have a focus at the origin and the directrix is perpendicular to the polar axis. and they have this form R equals EP over 1 minus E cosine theta. That E is the eccentricity, not the Euler's number E for exponential functions. That's the eccentricity. Okay, and so you get this basic formula. If the absolute value of E is 1, you get a parabola. Absolute value of the E here, so absolute value of E here is the actual eccentricity. If this absolute value E is between 0 and 1, you get an ellipse. If it's a slightly different formula here, just R of theta equals R, or R equals a cosine theta, that is a just circle centered at the origin. And then if you have R is again the same formula with eccentricity greater than 1, you get the hyperbola. Foci, here the formula for the foci. Here the formula for the directrices. We talked about the one here for parabolas. Turns out that ellipses and hyperbolas have them as well. There's the formulas with it. I'm not going to worry about too much. The center is going to be the origin for the basic one here, and then translated then to the point HK. There is no real center to a parabola. Instead, you have a vertex HK. If we call the leftmost and rightmost points and the topmost and bottommost points on an ellipse vertices, then these are the coordinates for that. X plus or minus a, comma k. Let me say it again. H plus or minus a, comma k. And then H plus or minus, let me say it again. I'm getting it wrong. H plus or minus a, comma k will be the left and rightmost points, and the top and bottommost points will be H, comma, K plus or minus B. Again, I'm always associating A with X and B with Y, and H with X and K with Y. A circle doesn't make any sense. Every single point's basically the same on that one. If the negative's on the Y square, then the vertices are going to be H plus or minus A, comma, K. If the negative's on the X squared term, it's going to be H, comma, K plus or minus B. The axes of symmetry are going to be vertical and horizontal when the setup we're looking at. And if the parabola is linear on Y, so it'll be x squared, be a vertical line, it'll be x equals h, okay? And linear on x, that's going to open left and right. It'll be a horizontal line of symmetry, y equals k. So it goes through the vertex either way. X equals h and y equals k will both be lines of symmetry for the parabolas and hyperbolas, both a horizontal and vertical line going through the center. And any line through the center will be a line of symmetry for a circle. They have a reflective property for a parabola. Light from the focus is reflected parallel to the axis of symmetry. Light coming in parallel to the axis of symmetry will converge on the focus. That's useful for making things such as satellite dish antennas and flashlights. For an ellipse, light from one focus is reflected through the other focus. That's useful in making something like a whispering gallery, for example. For a circle, light from the center is reflected back to the center. For a hyperbola, light going toward one focus and striking the outside of the hyperbola will be reflected toward the other focus. There are no asymptotes for parabolas, ellipses, and circles, but they are asymptotes for hyperbolas. The equations will be y equals plus or minus b over a times parentheses x minus h plus k. Notice it goes through the point hk, and it has slope minus plus or minus b over a. You have one each. There's two of them there, one with positive b over a and one with negative b over a. And that pretty much concludes basic conic sections, but I do want to point out there are some degenerate forms. It can degenerate to no solution, and one way you can see that is you look at this G here, given by this formula. If it's less than 0 and the product of A and C is 0 is positive, then there's no solution. If the product of A and C is positive and this G equals 0, then it generates to a single point, which is HK, and it's also minus D over 2A, comma, minus E over 2C. It degenerates to one line. That's pretty easy to see. If the A, B, and C are all 0, then you're just left with dx plus ey plus f equals 0. If you want to put that in the slope y-intercept form and solve for y, that is y equals minus d over e x plus f over e. And it degenerates to two lines when a times c is negative and the g is 0. So notice a times c is positive. That usually gives you uh, a uh, usually gives you an ellipse, right? Okay, and specifically when they A and C have the same sign, you get an ellipse, uh, assuming the B is 0. And if they're the same, you get it degenerates to a circle. If they're the same, but this G is 0, then it degenerates all the way down to a single point. That's like a circle or ellipse, it has a 0 radius, like a circle with 0 radius. And then if the A times C is positive, they have the same sign. Normally you'd think of that would give you an ellipse of some kind, possibly a circle. If the G is negative, then that's basically boils down to you've got, a square of something equals a negative. It's not going to be possible, so no solution at all. This one clearly, if you get rid of all the quadratic terms, you're all linear. That's a line. And then this one over here, when A times C is negative, that would normally be a hyperbola, which has a pair of asymptotes. And basically, when this G is 0, it degenerates down to where you're just left with the two, what would have been asymptotes, since you get a pair of intersecting lines. So conic sections are important geometric objects that were studied by the ancient Greeks. They're also important in the development of calculus, and they're typically studied in Calculus 2 as well as in pre-calculus and geometry courses. But our main reason for including them in this specific chapter is that they give an excellent example of an application of applying transformation of functions to relations in x and y, where y is not necessarily a function of x. And these same techniques can be applied to any relation x and y. So you might experiment by going to, say, GeoGebra or some other graphing utility and typing in an arbitrary relation in x and y. Wouldn't necessarily have to be a function if your software allows you to do that, and then making modifications to the formula to see how the graph is affected. So, if you replace x by x minus 3, it should still shift to the right 3 regardless of what formula you type in. And that's true whether it's a function or not a function. Okay, so that gives you a good little introduction to conic sections. There's more you can do with them, but that's a pretty thorough first look at them.